Recording.
Yo, dude, I'm not ready yet.
Just go. Just go.
Okay. Well, at least I have my ice ball and orange juice. And speaking about ice balls, this video is going to be about spheres. More specifically, the volume formula for spheres, 4/3 pi r cubed, and where the factor of 4/3 comes from. So I learned about the volume of spheres back in, I'd say, 5th grade, and I've always been curious on where the factor of 4/3 comes from until recently. So I decided to make this video explaining the origin of the factor of 4/3 in the volume formula for spheres. So as you can see, we have our sphere in Blender, and we're just gonna slice it in half. So now we have a hemisphere. So if we are able to show that the volume of this hemisphere is 2/3 pi r cubed, then we know that the volume of a sphere is 4/3 pi r cubed. Now to do this, let's start by enclosing our hemisphere with a cylinder. As you see, the radius of the hemisphere and cylinder are equal, or the same, and the height of the cylinder is equal to the radius of the hemisphere. Next, we place a cone into our cylinder, but just so that things don't get too messy, let's move the cylinder a bit to the right like this. So as you can see, we have our cone placed into our cylinder. Now, the radius of the cone is the same as the radius of the cylinder, and the height of the cone is also equal to the height of the cylinder. And remember that the height and radius of the cylinder is equal to the radius of the hemisphere. Okay, so now you might ask, Charlie, why are you talking about cones and cylinders when you're trying to show that the volume of a hemisphere is 2/3 pi r cubed? Well, the volume of a cylinder is base times height. The area of the base in our case is pi r squared, and the height of our cylinder is going to be r, the radius of the hemisphere. So therefore, the volume of the cylinder is pi r cubed. Now, the volume of a cone is 1/3 base times height. And the base, once again, is going to be pi r squared. And the height is going to be the radius of the hemisphere, r. So therefore, the volume of the cone is going to be 1/3 pi r cubed. Now, notice that the volume in between the cylinder and cone will be the difference in volumes of the cylinder, pi r cubed, and the cone, volume of the cone, which is 1/3 pi r cubed. So therefore, the volume in between the cylinder and cone is 2/3 pi r cubed. And actually, that's what we want to try and show that the volume of this hemisphere is. So, in a previous video, where I think it was about where the factor of 1/3 in the volume formula for cones comes from, we did something similar to this, and we did it slice by slice. So we got our sliced versions right here. Let's switch to rendered view. And we can also close these off. We won't be needing these anymore. Let's take a sip of our nice orange juice. Now, notice that if we show that at corresponding heights, the area of these circular slices that we made in the hemisphere are equal to the area of these, I don't know, donut-shaped slices in between the cylinder and cone, then we could conclude just by common sense or Cavaliers principle that the volume of the hemisphere is going to be equal to the volume in between the cylinder and cone. So, now, how are we supposed to do that if we don't know the volume formula for a hemisphere? Well, that's what the remainder of the video is going to be about. It's going to be about showing that at corresponding heights, the area of the slice of the hemisphere is equal to the corresponding height of this area in between the cylinder and cone. So let me switch to my iPad right here. And okay, so we have two pictures, one of which is our hemisphere and our cone and cylinder. We also have another picture of like a close-up in our cone and cylinder. So notice that if we go up, let's say at the circular slice, let's switch to the color white. Let's say that we go up by, I don't know, h, so the circular slice is from a height of h from the base, and the radius of our hemisphere is r, and therefore this length right here, which is the radius of the circular slice, is just going to be, by Pythagorean theorem, r squared minus h squared. Now, therefore, the area of the circular slice is going to be pi r squared minus h squared. Let's take another sip of orange juice. Okay, so now we already know that the outer circle area corresponding to our cylinder is going to have an area of pi r squared. But we need to find the area of this inner circular slice associated with our cone to be able to find out the area in between the cylinder and cone at the corresponding height to our hemisphere's height, which is h. Okay, so to do this, we're going to use our, I guess, zoomed in photo of our cylinder and cone, which is right here. And remember that the height of the cylinder and cone is r, the radius of the hemisphere. And also remember that the length of, well, not the length, but the radius of both the cylinder and cone is also r, the radius of the hemisphere. So therefore, this face associated with the cone is going to have a slope of 1. Okay, that was a bad triangle. Let me redraw that. So, it's going to have a slope of 1. And therefore, if we go up from the apex by, let's say, a height of h, that means that we go horizontally by h. And that's going to be the radius of the inner slice. So the radius here is going to be h. So therefore, the area of this slice is going to be pi h squared. Okay, so now the area of the slice in between the cylinder and cone at the height of h is going to be pi r squared minus pi h squared. And voila! That is equal to the area of the circular slice course of our hemisphere. And therefore, since they are at the same height and have the same area, then we can conclude that the area at every single slice is going to be equal. And because of common sense or Kavler's principle, we can conclude that the volume of our hemisphere and the volume in between our cylinder and cone are equal. And the volume in between our cylinder and cone is going to be the volume of the cone, not the volume of the cone, the volume of the cylinder, base times height, so that's going to be pi r cubed, minus the volume of the cone, which is going to be 1/3 pi r cubed. So therefore, the volume of this hemisphere is 2/3 pi r cubed. And because of that, the volume of a sphere is 4/3 pi r cubed. Now, if you're interested on how these models and animations are made using Blender, consider subscribing so that you would be notified when that video comes out, because I'm going to be working on a video about that. So yeah, thanks for watching.